Good. So we're scheduled to cover chapter 17 today, which is on amino acids, polypeptides, and by extension, proteins. Although a lot of the sections of this chapter you're not going to be responsible for. I wrote that down in the class notes, which sections you're not responsible for. Those are going to be the sections that focus heavily on biochemical and biological function. You'll have covered that already in your biology classes anyway, and I don't think it's appropriate for a chemistry course. So as always, we're going to focus on mainly structure, I would say, since as you'll have noticed by now, we organic chemists are kind of obsessed with structure. So we'll talk about the structure of amino acids with particular attention to how that varies depending on pH. And I'll even say right now, the three pHs I'm really going to care about are 1, 7, and 14. So strongly acidic, neutral, and strongly alkaline. I know there are some evil owl questions where they say at pH 10.3, you know, they're purposely trying to be evil. I don't care about evil pHs. Only 1, 7, and 14. Those are always clear, as I hope to establish today. So that's what we're going to cover today. It might be kind of a short class, we'll see. I will certainly do my best not to rush, but if we end early, we'll end early. I feel like Friday's class, even especially given if I cover all of polymers, I feel like that class will be less short than today's class. But I still really think I'll be able to cover all of polymers on Friday. And so if so, then class on Monday and Wednesday will be replaced with extended office hours. And I'll just be in my office during, or if I'm not in my office, I'll be somewhere on the hall and I'll leave a note on my office door. So, but I will certainly make myself available on Monday and Wednesday if anyone wants to go over anything or that kind of thing. Good. So let's see. As you might be aware, the proteins that make us up, that are structural proteins, also that are enzymes are proteins also, contain 20 different amino acids. There's a list of all of the amino acids and their structures in your book. You do not, repeat, not have to memorize all those amino acids. I would never do that to you guys. I would expect you to be able to draw an amino acid or even a small polypeptide given enough information, on the side chains of the amino acids. And we'll build them up slowly today. We're going to start with individual amino acids, and then we'll cover how they go together to make polypeptides and then by extension proteins. But you certainly do not have to memorize all 20 amino acids. If you go on to take a biochem class ever, you probably will get that pleasure. That's something generally you have to do in a biochem class, not here. I don't think that would be appropriate at all. So let's talk first just generally about the structure of amino acids. We already know about amines. We covered amines in chapter 11. So an amino acid simply contains an amino group and a carboxylic acid functional group. I'm okay abbreviating carboxylic acid functional group CO2H, right? You can write COOH if you like. That's another acceptable abbreviation. But a typical amino acid would look something like this. Well, sort of. I'm kind of lying, and we'll say why that is. This is the structure a typical amino acid would take in the gas phase. And we're not normally dealing with things in the gas phase, especially in living systems. We're used to things being in aqueous solution. So we're not dealing with gas phase molecules. The structure of an amino acid would vary depending on the pH. So let's look first at the structure of an amino acid where R is the side chain. That's how it would look at pH equals 1. So again, assuming that there's no ionizable groups in the side chain. We'll give examples of that later on as well. But at pH 1, we're below the pKa of the carboxylic acid functional group. So the carboxylic acid still has its proton on. We're also well below the pKa of this amino group. So it's going to be protonated. So again, in those cases where R is not ionizable, you'll find that the total charge on an amino acid molecule will be +1. At pH equals 7, that's the intermediate case. At pH 7, we're going to be above the pKa of the carboxylic acid functional group. That carboxylic acid functional group will have a pKa generally round and about 2.5. And I should have mentioned the ammonium group, those generally have a pKa round and about 9.5, somewhere in that range. Could be 9, could be 10, but somewhere around and about that. So at pH 7, we're intermediate between those two pKa's. We're still below the pKa of the ammonium group, so that's still going to be protonated, but we're now above, we're more alkaline than the pK of the carboxylic acid functional group. So that will now be deprotonated. Let me see if I can, oops, I didn't mean to do that to chat. We'll move chat over a little bit. And finally, at pH equals 14, I screwed that up already. At pH 14, we're above both pKa's. So the ammonium group is going to be deprotonated and we'll have the amine-free base. And of course, we'll still have the deprotonated carboxylic acid. That's how a typical amino acid will look at pH equals 14. So that's the pattern to bear in mind. Again, it's going to depend a little bit on what R is. There's 20 possibilities for R, and as I said, you don't have to memorize those 20 possibilities. If you take biochem, you'll probably get to enjoy that, but if you're done with biology and biochemistry, you're probably safe from having to memorize those, because I'm certainly not interested in making you memorize those in this class. Good. So the first thing to focus on is what pH we're at, and that's why I'm giving you the general state of these types of molecules at pH 1, at pH 7, and at pH 14. It turns out those three pHs are very clear. It's always possible to tell what the state is of any given functional group at those three pHs. I wouldn't try to give you anything tricky or intermediate or strange, but those three pHs, everything's very clear. Another thing I forgot to mention is you'll notice that we do have a chiral carbon atom here. If this were Chem 228 rather than Chem 222, I'd also make you learn how to draw it showing the correct stereochemistry. I can't see any upside to making you learn that. I think that would be just extra busy work, and I want to avoid busy work as much as I can anyway. I would like you to learn things that actually have a point, and I don't see how that would do you any earthly good at all. So, but of course, do bear in mind that this carbon is chiral. There is only one achiral amino acid where R is hydrogen. And in that case, at that carbon, you have CH2, and that's no longer chiral. That amino acid happens to be called glycine, and perhaps you've heard of it. But yeah, there is a chiral carbon, but let's not trouble ourselves with that. Good. So let's get into some particular examples of amino acids. Let's look first of all at an example of an amino acid with a non-ionizable side chain. And let's draw it at pH equals 7. This is the other type of pH. So this happens to be phenylalanine. Again, I don't really care if you memorize that. At pH equals 7. And you can see that we followed the pattern over here. The ammonium group is protonated, the carboxylic acid is deprotonated. And there's nothing on the side chain R that's going to change with pH. There's no ionizable hydrogens on that group. If instead, though, we had something like aspartic acid. Oh, wait, before we get to aspartic acid, let me just state that at pH equals 1, of course, we'll put the proton back on the carboxylic acid functional group. So at pH equals 1, I guess the total charge in the molecule would be +1. At pH 7, the total charge is going to be 0. And at pH 14, we'll deprotonate the ammonium group and get the amine-free base, NH2. And then the total charge on the molecule will be -1. So that's nice and clear in cases like with phenylalanine, where the side chain is not ionizable. With an amino acid like aspartic acid, however, there the side chain is ionizable. In fact, there's another carboxylic acid functional group on the side chain. But at pH equals 7, this is aspartic acid. Again, I don't really care if you memorize that. I still have some of them memorized. I had to learn them approximately 1,000 years ago, but I still have some of them memorized just from teaching it, I guess. But you don't have to memorize that. Anyway, at pH 7, we're going to be below the pKs of both of those carboxylic acid functional groups. Remember, those are going to be around 2.5. So at pH equals 7, we're above that. We're more alkaline than the pKa of the carboxylic acid functional group. So they will both be deprotonated. We're still, however, below the pKa of the ammonium group. Remember, that's around 9.5. So we're more acidic than the pKa of the ammonium group. So that's going to be protonated. That's going to be in this form. So I guess at pH equals 7, let's play the game again. What's going to be the total charge in the molecule? I guess -1 in the case of a molecule like that. At pH equals 1, both of those carboxylic acid groups will be protonated. So they'll be CO2H, both of them. And then I guess our total charge will be +1. Meanwhile, at pH equals 14, of course, our carboxylic acids are still deprotonated, but so will be the ammonium group. That will be NH2 instead of NH3+ at pH equals 14. And I guess our total charge there would be -2. Oh, I'm mentioning charges in part. You'll see that mentioned in the book. The book covers like electrophoresis and things like this. Of course, you're not going to be responsible for that. That has its place in the biology class, I think. But the total charge in the molecule does matter for certain experimental techniques. I guess we'll just leave it at that. I think that's all we really need to say. To give another example of an amino acid with a positively charged side chain, this one happens to be lysine. I think lysine is a total of 6 carbons, 3, 4, 5, 6. Yep, 1, 2, 3, 4, 5, 6. So this is going to be lysine at pH equals 7. And you'll notice again, at pH 7, we're more acidic. We're below the pKa of those ammonium groups. So they will both be protonated. At pH 1, the carboxylic acid functional group will also be protonated. It'll be CO2H instead of CO2-. And then, of course, at pH 14, the carboxylic acid group is still deprotonated, and both of the ammonium groups will now be amine-free base groups, NH2 instead of NH3+. So that's how the structure of these things varies depending on the pH. And that's one of the main topics that I really wanted to focus on when it comes to amino acids. And that's going to stay true when we start putting these guys together and making, say, a dipeptide or a tripeptide. I would expect you to be able to draw a small polypeptide as well, say 2 or 3 of them. 10 is too many. 2 or 3 is reasonable. Good. Any questions so far then? Well, I don't want to spend a lot of time talking about isoelectric point, but I want to at least mention it since, probably 90% of the time, it's really easy to calculate. But the isoelectric point is the pH at which the overall charge on the whole molecule is 0. It's going to, so pH at which the overall charge on the sample as a whole let's say on the molecules in the sample. So again, considering all of those molecules all at once is 0. And in general, that's pretty easy to calculate. at least in those cases where the side chain, this R group, is not ionizable, like in phenylalanine. In that case, all you need to do is average the pKa's of the carboxylic acid and the ammonium group. So it would be the pKa of the CO2H group plus the pKa of the NH3 plus group divided by 2. So of course, I don't expect you to memorize pKa's either. Except it would be really great if you knew that the carboxylic acid is around 2.5 and the ammonium group is going to be around 9.5. You can look them up and you'll see they're in general pretty close to that. So it's going to be the average of those two values if side chain is not ionizable. Which I believe over half the time is going to be the case. So you can already see that if the pK of the carboxylic acid functional group is 2.5, the pK of the ammonium group is 9.5, just going on average values there. 2.5 and 9.5 is 12. 12 divided by 2 is 6. You don't even need a calculator. So most of the PIs are around 6. It's a little bit more complicated if you're dealing with ionizable side chains, like in aspartic acid, like in lysine. That's a little more complicated. And that would be something, if you need to know that, I would expect you would cover in an upper level class. But certainly for those cases where the side chain is not ionizable, it's straightforward to calculate. You just would be given the pKa of the carboxylic acid functional group, you'd be given the pK of the ammonium group, and you'd average them. You'd add them up and divide by 2. Don't even need to calculate it, you can do it in your head. So I didn't want to spend any more time than that on it, but that's all there is to the isoelectric point. Let me erase all these. Good. Well, what about reactions of amino acids? Well, as I said, we've already done a chapter on amines. We've already done a chapter in carboxylic acids. So we know the types of reactions that amines can undergo. The amino group in amino acids can do the same sort of things. And we know what sort of reactions carboxylic acids can undergo also. The amine chapter, I think, was chapter 11. The carboxylic acids chapter, the chapter that covered carboxylic acids at least, was chapter 10. We recently covered it. So that's partly why I put the amino acids chapter at this point in the term, because now we've covered the chapter on amines and the chapter in carboxylic acids. So it seemed to make sense to put this chapter here. But the carboxylic acid functional group can undergo the same types of reactions that other carboxylic acids can undergo. For example, I meant to write reactions of carboxylic acids, or reactions of amino acids. Can I go RxNS? So for example, let's take a simple amino acid. Let's take alanine, where the side chain is just a methyl group. In case you're curious, that's called alanine. I don't really care if you memorize that. We already know that carboxylic acid functional groups can be esterified using the Fischer esterification method. We would simply take an alcohol, like maybe methanol, and add an acid catalyst. And in so doing, this will become the ester. Whoops, actually will be H2N at this point. So instead of a carboxylic acid, it will be the methyl ester. And our methyl group down here. So notice that the amino group notice that the ammonium group goes back to the amino group because this is no longer a carboxylic acid. There's no longer an extra proton around to protonate the amino group, because that's really what happens in at pH 7. Is the amino group pulls off the proton from the carboxylic acid, but now there's no longer a carboxylic acid functional group, so there's no extra protons around. You would also, I guess, get a molecule of water out of this, plus water. So this is Fischer esterification, which we covered in chapter 10. So that's a reaction we know about already. And I even gave you in the class notes, I gave you which sections you can look at in order to review that. Likewise, the amino group will do the same types of things that any other amino group will do, including undergoing nucleophilic acyl substitution, just like we talked about in chapter 10. So let's take alanine again. And if we were to treat this with, let's say, acetyl chloride, any acid chloride or acid anhydride, this is now going to put the acyl group onto the nitrogen. This now will be CO2H because there's now no amine in order to that can accept that extra proton. This is now an amide, not an amine. And so amides, as you may recall, are significantly less alkaline than amines. So you won't be protonating that nitrogen. But let me get a color going over here. So this acetyl group will come from the acetyl chloride. That's a chapter 10 reaction also. So all this is to say that the amino group and the carboxylic acid group do exactly the same chemistry as they would do if they were not in the same molecule. Same types of reactions. Good. Questions on that then? Yes. Mm-hmm. Yes, it might not be this exact same proton, but it's going to get it from one of those on some molecule. And again, the reason is, I should say for the sake of chat, the question was, where did this H come from and why is this no longer protonated? Remember, amides are much less basic than amines. So that's the reason why you're not going to protonate that nitrogen. Not with a carboxylic acid anyway. You need a much more, is that kind of what you meant? Yeah, that's right. This is no longer has a plus charge. Oh yeah, that's a good way of thinking about it. That you do get HCl. I maybe should even say that. HCl. Yep, that's your inorganic side product. So if you wanted a balanced equation, you'd also mention the HCl. Yep, that's right. But yeah, carboxylic acid is nowhere near a strong enough acid to protonate that amide. So you see how we tend to forget about the inorganic side products. We consider them largely irrelevant. But yes, you do make HCl also. Other questions? All right, well then I guess my only other topic that I really want to talk about is how to put these things together. And make polypeptides. Maybe before I get into particular examples, let's deal with general cases. Maybe let's take I'm just going to make two generalized amino acids, and I'm going to call their side chains R1 and R2. I wish I'd used another color. Well, we'll work it out. What's going to happen is that you're going to form an amide with the carboxylic acid group on one of the amino acids and the amino group on the other. Similar to how we made an amide over here. That's again just a chapter 10 reaction. So what you wind up getting will look like this. This, by the way, is pH 7. And R1 will go over here. R2 will go over here. So let me at least point out some of these atoms. The carboxylic acid carbonyl carbon is over here. And the amide nitrogen is over here. So that's where those atoms originally come from. And you would also, I guess, get a molecule of water. But that again is a chapter 10 reaction. That's essentially forming an amide from a carboxylic acid and an amine. So you just link those two groups together. And then one could imagine a carboxylic acid group of another amino acid coming along and forming an amide here. And then again, then again, then again. One could imagine an amino group from another amino acid coming in over here and making an amide. Then again, then again. So you can see this can go on as many thousands and tens of thousands of times as you want. And that's how you go from a small polypeptide to a protein. And although we're certainly not going to be drawing anything with 10,000 amino acid residues, I think you can already see how that would be built up. But drawing a simple polypeptide with maybe 2 or 3 amino acid residues would be something that I would expect you to be able to do. There's a sample problem in the class notes where I gave the side chains of 2 different amino acids, serine and glutamic acid, and then asked you to draw that polypeptide of those 2 in order. By the way, you'll notice there is an order. If you switch R1 and R2, you get a different compound. So it does matter what order you put them in. Generally, by convention, we start at the nitrogen atom. That's just sort of the conventional way of drawing polypeptides. You move from the nitrogen end to the carboxylate end. So that does matter, the order that you go in. In other words, if you switched R1 and R2, you'd get a different dipeptide. It would be a different compound. So maybe since there's one already in the class notes, let me make up a different one. Let's draw, and this would also be at pH 7. Oh, what amino acids do I like today? Let's do alanine, since we already have it up there, followed by, we already did aspartic acid. Kind of a fan of serine, but we've already used it. Oh, I don't know, threonine. And I'll tell you the side chains. And we'll do that at pH 1, 7, and 14. And then we'll call it a day. So alanine is a side, I'll even just give you, I could just give you the side chains, or I could just give you the amino acids themselves. Alanine just has a methyl group. That's how it looks at pH 7. Threonine looks like this. At pH 7. So what we would do, I'm going to kind of try to draw pH 7 in the middle, since I think that will make the most sense. So we'll go to the carbonyl group of the alanine molecule. That's going to have our methyl group, then NH, and then CO2 minus at the other end. That's going to be pH equals 7. And you see, once again, we formed an amide functional group. You're just taking the carboxylic acid group of one amino acid and the amino group of another one, bringing them together to make an amide plus a water molecule. So that's how that would look at pH equals 7. At pH equals 1, I kind of picked an easy one, though, yeah, in many ways, I picked an easier one than in your class notes, because both of these side chains are non-ionizable. You're not going to be able to pull off the OH hydrogen, not even at pH 14. That pKa is probably around 18 or 19. So even at pH 14, you're not going to pull that proton off. Let's do it at pH 1, maybe. So we have a methyl group over here, and then the threonine side chain over here. That's pH equals 1. So same type of connectivity, but we also have protonated the carboxylic acid functional group. And then last but not least, maybe I'll put it down here. Oh, wait a minute, what am I doing? We're at pH 14 now. That's no longer protonated. We have our carbonyl from the first amino acid going to the NH from the second amino acid. And then CO2 minus over here. We've got a methyl group over here. We've got that threonine side chain over here. This is how the molecule would look at pH equals 14. So again, note the difference in the protonation states. At pH 1 and pH 7, we're below the pK of the ammonium group. So it's more acidic than the pK of the ammonium group. So that means the ammonium group will stay protonated at pH 1 and at pH 7. But at pH 7, or rather at pH 1, we're below the pKa also of the carboxylic acid functional group. So we still have the free carboxylic acid. We still have the H on the carboxylic acid at pH 1. That H is gone at pH 7 because now we're above. Remember, about 2.5 is the pKa of the carboxylic acid functional group. So at pH 7, we're above that. We're more alkaline than the pKa of the carboxylic acid functional group, but not the pK of the ammonium group. That's going to be around 9.5 or 10. So the ammonium group is still protonated, but the carboxylic acid functional group is deprotonated at pH 7. And then finally at pH 14, we're above all those pKa's. So everything is deprotonated. The ammonium group is deprotonated and you have the free amine. And of course, the carboxylic acid functional group is also deprotonated. So you have the carboxylate group. And let's see, we already talked about disulfides in the alcohols and thiols chapter. That was chapter 17. So I don't know that I need to mention anything about that. I know what else I can do. Since we still have time, let me at least give you the other answers to, since I asked a question in the class notes. I mean, I want you to at least have the answers so you can see if you did it right. In the class notes, we did much the same thing, but we drew serine glutamine. So let me draw that at pH 1. Not glutamine, glutamic acid, sorry. Move that up here, maybe. CO2H and CO2H. This is going to be serine glutamic acid at pH equals 1. So notice the carboxylic acid functional groups are also protonated. And then at pH 14, of course, the amino group will not be protonated. But I wanted to at least give you that in case you decided to work on that later. And of course, the carboxylate groups will also be deprotonated. CO2 minus, and I need my CH2OH over here. Here it is at pH equals 14. That way your class notes are complete. Good, can't really think of anything else. Questions on amino acids or polypeptides? We actually almost made it to 2:30, that's not bad. So I already know that class on Wednesday will be replaced with office hours. We'll see if I get through everything in polymers on Friday. I kind of think I will. I think the chances are better than 50%. So other than that, have a great day. We'll see you Friday.